Okay, so we are continuing our chapter discussion about signal, contrast and noise and its importance. So just like the previous classes, we'll have a few review slides and then we'll get into the topics of today's class. Excuse me. So in the last class we introduced the fact that of course any measurement will have noise associated with it, and that noise in our case is proportional to it's basically thermal noise proportional to the body, coil coupling with the object, and then the coil and then its electronics, etc. That's mostly driving our noise. Essentially the systematic and physiological noise we didn't particularly discuss, but they are nonetheless sources of some error. And the thermal noise happens to be proportional to, has this proportionality relationship, which is with respect to the time, the effective resistance of the coil, and then the bandwidth of your experiment. So essentially, this is the point of interest for us, bandwidth read being one of the parameters that you could change in your experiment. Now we made a note that of course this noise is actually appearing in the frequency domain, which is where we are sampling our data, or spatial frequency domain, or the K space, and it's important for us to understand what is its effect in the imaging domain. So along the dimension where you're doing at the Fourier transformation, it happens so that the noise standard deviation that in the K space domain is actually higher by 1 by n compared to the noise, or in other words, noise in the imaging domain, the variance in the imaging domain gets divided by the number of sample points that you're Fourier transforming, or that you're sampling and then for inverse Fourier transforming to get your image. That is along the dimension that you're doing your Fourier transformation. So the reason that I'm mentioning specifically that is when you have, let's say, non-Cartesian sampling, for example radial or spiral or any other non-Cartesian sampling, then the noise, you would have to see how the reconstructed noise would appear. In the rectilinear or Cartesian sampling, you essentially are sampling kx and ky along those dimensions, and you're doing two-dimensional Fourier transformation along x and y, and hence this relationship that's shown here is valid. Whereas for non-Cartesian sampling, you would have to evaluate that again, and actually it's been evaluated in other texts, so of course you just have to look it up, I guess. So now one further thing that we need to note, of course, is that the noise that we're talking about so far was actually in the real and imaginary channels. Even in the image domain, we're talking about real and imaginary channels, I mean SK being complex, right? So you can divide that into your, hold on, I think the animation got up and down, but so you have the real and imaginary channels. That's the noise that you have, the sigma measured square by n relationship that you saw in the previous slide is valid for one of those imaginary or real channels, because both of them are being Fourier transformed and then you get the value, right? Now, so what happens when you actually calculate, because you're looking at the data typically in a magnitude domain, you're not particularly looking at the data in real and imaginary domain. Part of the reason why is that because practically speaking, even though your object may be purely real, because of the imaging operations being non-ideal, you will have some phase component. So to avoid phase obscuring your interpretation of your image, you basically take the take the magnitude of your data and then observe that as an image. Of course, phase also has its own uses where you would eventually see that in the course of this course. But so right now we're talking about just the magnitude. Okay, again I think the animation got screwed up. Anyway, so you can actually calculate what happens in the imaginary and real channels. You have that sigma, meaning noise variance or noise standard deviation. What is the effect of that noise in the reconstructed magnitude image. So because you know S mag is related to your I and R is reconstructed in this manner, you can use the error propagation equation to estimate what the noise in these individual numbers or in these individual variables leads to in the reconstructed magnitude. So you can use this expression where if m is a function of these variables, then you can evaluate the variance in m using this. It's essentially you can get this approximate relationship using the Taylor series expansion. So once you use that, you actually end up with this equation. If you do that for this, you end up with this equation that the sigma in the magnitude domain is actually equal to sigma naught, which is basically in our case we're assuming that noise in the imaginary channel and the real channel are uncorrelated and equal. For a given experiment, the sample noise variance doesn't change, but it's different for and it's uncorrelated in the imaginary and real channels, and hence we are using this relationship. You will end up getting this relationship. Okay, so that tells us that whatever individual noise that you're seeing in the image domain in the imaginary and real channels, you would get the same noise standard deviation in the reconstructed magnitude. Now there is a caveat here. This is actually only approximately true. It turns out that when you have really no signal at all, meaning your ideal signal is 0, in that region, remember we talked about the noise distribution being Rayleigh distribution rather than Gaussian distribution, right? So that is where you start seeing the difference, and essentially in the strictest sense, the noise distribution or probability density function can be described as a Rayleigh distribution, and depending on the ideal signal that you have, the magnitude of that, the distribution of that shifts, and that has been actually demonstrated in one of the early papers in '95, that if your ideal signal A is 0, then you have this Rayleigh distribution. The Rayleigh distribution turns to, that's a special condition of Rayleigh distribution where your noise is probability density function is skewed. You guys can see that, right? Okay. Now, as the value of your, signal value of your object, ideal signal, which is no noise case, is increasing, and hence the A by sigma ratio is increasing. As you see that ratio increasing, then the distribution of probability density function becomes more and more Gaussian. So that's what I was referring to yesterday when I said as long as the SNR is greater than we're all set? Okay. Oh, I see. That's probably why it's too cold as well. Well, maybe that's something to do with that. Anyway, let's get back to the class. You guys are okay back there? You're all okay? Okay, good. So that's what I was referring to in the last class, where this Rayleigh distribution turns out because your ideal signal is 0 here, and when you have signal, the noise becomes more Gaussian distributed, and you see that example here where you look at the subtracted image, you can make out the noise in the object is different from the noise outside. So as long as the SNR is greater than 3 to 1, greater than or equal to 3 to 1, your noise distribution can be assumed as Gaussian. And if it's less than that, then you would end up into that zone of Rayleigh or Rayleigh distribution. Okay. Well, again, I think we just have to do that. Yes, okay, let's do that. Now, this we haven't gone through in the last class, but because of continuity, not to lose the continuity, I just inserted this slide. This is actually pertains to what we are going to be learning, or what we are learning in this class. So we just talked about noise in the magnitude domain, but you're also reconstructing a phase image. So phase, of course, is defined by phi being tan inverse of imaginary and real, and that tan inverse is actually that it's actually going from minus pi to pi, right? So it's the 4-quadrant tan inverse, not the 2-quadrant one. You can use the same methodology that we talked about in the last slide, where use the same error propagation equation to evaluate what is happening to error in or noise in the variable phi as a function of noise in the imaginary and real channels. Once you do that carefully and you use this assumption that, again, we are sticking to the same assumption, the noise being equal in the imaginary and real channels, and the noise variance or standard deviation, and being equal to sigma naught. So your noise standard deviation in the phase domain is equal to the inverse of the SNR in the magnitude domain. And this is one of the important relations that you want to, well, if you're working in the phase domain, then you would want to remember. And again, this is true in general for good signal to noise ratio cases. Now imagine that S magnitude is 0, then obviously this relationship you're going to infinity, which doesn't stand. So like I said, this is only true for finite signal to noise ratios. And in fact, if you go back to the distribution, the Rician distribution, and then actually follow through that and look at what happens in the phase domain, you will end up with this kind of probability density function plot, where this 1, 2, 3 is your A by sigma ratio, and this is your phase. This is your probability density distribution along minus pi to pi. So I mean, because you're always mapping that to minus pi to pi, right? So that's why it is plotted as such. And as you can see, as your if your signal to noise ratio is a signal in the magnitude is 0, your noise probability density function is flat, meaning your sigma of your noise in phase is flat. So the standard deviation is constant, meaning the probability that that particular voxel will have a certain phase is equal, meaning it's pointing in every direction. If you can imagine, it has the probability to point in any direction, right? That vector that you're calculating the phase of. Now as your signal increases, you're getting more and more closer to your Gaussian distribution of phase noise, basically, right? It's centered around 0. I mean, basically it's Gaussian, mean 0 and finite standard deviation, non-zero sigma. Everybody clear on that? So essentially, sigma phi is 1 by SNR of magnitude. Okay. Now again, this is also actually, forgot to put the citation here, but this is also from the same paper as the previous one that I mentioned. Okay, let's come back to what we discussed in the last class again. So we saw that the signal was proportional to the voxel volume. This we just saw, it's inversely proportional to the standard deviation of the noise is inversely proportional to the number of points you're sampling along the Fourier dimension. And again, if you're averaging the same kind of effect of inverse square root and the reduction in the noise, and of course we started with this relationship of where noise was being proportional to the square root of the bandwidth readout of your experiment, and we combined all those. We ended up with this relationship where this is telling us what would the change in the SNR be if you change a certain parameter relative to the other ones. And of course you have to remember that all the Nyquist relationships, everything still hold, and if you substitute all of those, I mean, you can substitute for different variables in that expression and then come up with different expressions for SNR per unit voxel, different proportionality expressions. Okay, and then we looked at contrast to noise ratio, the contrast being more important, as we said that, well, you can image all you want. If you're not able to distinguish between the different tissues that you're imaging, then getting a flat image is as good as getting no image. Well, in terms of its usage, basically, right? So contrast, of course, is important, and we'll be talking about how to generate contrast and how we are generating contrast in MR and all that. But in the presence of noise, being able to distinguish one signal from the other also becomes important, and that's where contrast noise measure comes in, which is basically the difference of the signal to noise ratios of those two tissues. And we looked at the visibility and the Rose criteria, where we said that if the object is occupying quite a few voxels, then your visibility more or less remains. Basically, if an object has more number of voxels, even if the signal difference is small, you will still be able to see it, because it's as if you're making that measurement in each voxel, and so that's n number of times. So your effective CNR, which your eye is already doing, averaging in your mind, is basically multiplied by square root of number of voxels, and that becomes important or apparent here, where we saw, well, the intensity was changing in this direction and the object size was changing in this direction. As you can see here, contrast to noise ratio, object size is same, but because of the signal difference is small here, you're not able to see it, but it's quite, signal difference is sizable, so you're able to see it. Now again, here, for the same signal difference, you're able to see the object for a given finite size. If the object is smaller than on that size, you're not able to see that because of that square root n effect, the number of voxels effect. Everybody get that right? Okay, good. So now we're jumping to today's class topics, where we're talking about contrast and its optimization, and we'll see, we'll talk about partial voluming, and then effect of exogenous contrast agents. Okay, so MR, as you might already have known if you're at least exposed to some part of that imaging, can generate quite a few types of contrast. Some of the basic types, of course, is the spin density, T1, T2, T2 star, T1 rho, diffusion, chemical shift, susceptibility, temperature, etc. These are intrinsic material properties that can affect your signal, and you can see from your block equations that rho naught and T1 and T2 are already there in your block equations, right? And actually, in fact, diffusion is also there, but we haven't considered, it's not block equation, it's Bloch-Torre equation, but we didn't consider that. But that's also, you can include the diffusion term also in your the empirical block equation. And I think that's called the Bloch-Torre equation. Okay, so those are the intrinsic material properties that would affect your signal, and you're able to generate contrast. And you will also see that physiological effects like flow and perfusion, blood oxygenation, etc., which are actually dependent on these tissue properties. The basis, of course, is this, but you can generate from this, you can generate contrast based on these by actually modifying your mode of acquisition, your experimental design, basically. And then by using different experimental designs or sequence designs, you could actually do different types of imaging. You can select or selectively suppress the tissue, or do steady state imaging. And so the other options are basically just selecting and nulling the tissue. And there are other types of contrast, as you will see them being discussed in the course of this course, basically. Okay, so like I said, the basic contrast is already the basis of generating contrast is already there in your block equations, where you have M, which is your magnetization, which is actually it has all these other terms of spin density of your tissue embedded within that parameter. And then you have T1, which is your T1 longitudinal relaxation of your of the sample, and then T2, which is the transverse relaxation, transverse decay of the sample. So these, the rho or spin density, T1 and T2 are the basic contrast mechanisms that your signal is going to be dependent on, as the block equations is telling us, right? So I'm not those, and then so T1 and T2, the different tissues have different relaxation properties, and that's basically the basis of how you can actually generate contrast between these tissues. So as you can see, these are given in milliseconds. So gray matter, these are at 1.5 T. It's about 1000 gray matter. White matter is about 600. Muscle almost closer to the gray matter. CSF has the largest, which is more or less equal to water, which is 4500 milliseconds, which is 4 seconds, and 4.5 seconds. And then fat has a very short T1 compared to all these other tissues. And then blood is slightly higher than your gray matter. And if you see, there is quite a bit of correlation between your T1s and T2s. The larger the T1, the larger the T2 as well, typically. Except for muscle, that's a bit.
White matter and muscle, 600, 900,
See, CSF, largest T1, it has the largest T2. Gray matter, the next largest. Well, blood is the next largest, which 100 and 200 is basically for venous and arterial. So, so if you consider arterial, T1 is same for both, more or less, and T2 is, well, T1 is also actually not same, but that's a caveat. But anyway, let's consider arterial, which is about 1200 blood, and arterial T2 is about 200, and then you go to the next one, which is white matter at 600 T1, that's 80. So far we are linear, more or less, right? Decreasing, the lower the T1, the lower is the T2, and suddenly muscle and fat are a bit different. Of course, these properties depend on the tissue microstructure. So, but this is kind of a general empirical rule that I'm mentioning. It's a rule of thumb typically that if you have a large T1, means that you have a lot of water, means that your T2 is going to be longer.
Solids in general have
Shorter T2s. Solids, T2s are shorter. T1s, I'm not particularly sure. I don't remember exactly. T2s definitely are very short. They're on the order of microseconds. So, for example, if you do this very nice experiment, I wish I had these images, but we did this experiment. So, if you put ice and in the magnet, and then you start doing the experiment, initially, if it's just ice, then you won't get any signal. Your scanner will not run any scan because it doesn't get any signal. Then slowly it will start melting, and then slowly the coil is able to pick up the signal and then say, okay, there is some water, so I can image it. Now you will start seeing wherever the ice had melted, you will see the signal, and wherever there is ice, you won't see any signal. That's because your TEs, echo times, where you're actually getting your center of K-space signal, are on the order of few milliseconds, whereas the T2 of the ice is on the order of microseconds. So you won't be able to see it unless it melts. Actually, we did that experiment. Well, we could always do that again, I guess. But anyway, so let's come back to our contrast discussion. Now, just these kind of cartoons are just to remind you that how we are doing this imaging. We are doing this line by line. So you're doing multiple excitations and readout of your K-space, right? Of course. And each time you're tipping the magnetization, you have the longitudinal recovery. So effectively, this is the type of experiment you're doing. And your TR is going to determine how much your longitudinal magnetization has recovered. In this case, the excitation is 90 degrees, so the transverse magnetization has been, the longitudinal magnetization has been completely tipped into the 90 degree transverse plane, which is the case we have already gone through quite a few times in our class, right? So your signal is given by, the top equations are essentially your block equation solutions for transverse and longitudinal magnetizations, right? And so for a 90 degree case, your MZ after the second TR, actually, yeah, just before the second excitation pulse, TR minus is that M naught into 1 minus e power minus TR by T1, which is, if you call this as E1, typically to kind of save ourselves the trouble of reading that out completely, we call that E1, and this is E2, E1 being the TR, TR by T1, I mean this is referring to this term, this is referring to that term. So that gives you the longitudinal magnetization and your transverse magnetization signal. Basically, this is the signal that you're getting, right? Now, the reason why we're going all of this is that now this has to do with the contrast discussion. So M0 is your spin density, T1 is your longitudinal relaxation, and T2 is your transverse decay rate, right? So your signal is being weighted by all of them. Now, well, this is true under this assumption, so you just have to remember that. Well, if you have done this problem right in the exam, then you would realize that. Anyway, so it's basically all of the contrast discussion is the following contrast discussion is going to be based on that equation, this equation, because that's the signal that you're getting in your experiment where you're doing 90 degrees and then reading out the data, right? Okay, so this is your the signal recovery. Let's take 3 tissues which have different T1s and different T2s. So if you remember the T1 values, white matter is about 600, gray matter is about 950, CSF is about 4500, right? And T2s are, I think, what was that? White matter, CSF was 2200, and then white matter was 80, and then gray matter was about 100, isn't it? Right? Approximately. So those would be affecting your contrast, right? So let's see in your multipulse experiment how this particular recovery and decay are going to affect your signal, or in relation to your experimental parameters, how are they going to give you different weighting. So different tissues have different longitudinal spin densities, and if you wait long enough after your excitation, the longitudinal magnetization at t equal to 0, as soon as you tip it, is proportional to your spin densities, or effective spin densities that we went through in chapter 9, I think, right? So at t equal to infinity, once you tip it and then you let it recover, that's same as t equal to 0 when you excite, just before you excite. So t equal to infinity, where it's completely recovered, it's this part that I'm talking about, where this is basically your spin density weighting, or spin density your M0. So if you want to actually get your get your image weighted by M0, then you can sample at this point along its recovery curve and get your signal. But then once you tip it, this is your T2 decay, right? So you don't want your signal to be weighted by this, so you want your echo time to be very short. As soon as you tip it, you want to as quickly as possible sample your K space. So that tells you that what does that give us? It gives us the signal or image which is weighted by the differences here that we see, which is based on your spin density of your tissue, right? So in terms of the equation, just to kind of remind you, if t tends to be 0, it tends to 0, this would be 1. Essentially, you're imaging M0. So that's what you would get in spin density weighted image. This is basically rho naught weighting, and the condition for that is long TRs. So basically, you're allowing your magnetization to recover enough to reach steady state. Typically 5 times the T1 value of your tissue, of the largest T1 tissue with the largest T1 within your sample. So imagine if you're doing this for CSF in brain, and you're doing that for, let's say that's 4.5, let's say 5 for our calculations, so that's 25 seconds of TR. So you wait every 25 seconds, you're going to get a K space line to get pure spin density weighting. Of course, that is impractical, which is why we use a little bit shorter TR on the order of the equal to T1, which is why you don't see this CSF being really bright. Otherwise, you should see CSF really the brightest in this image. But practically speaking, we use T1 TRs on the order of 2 T1s typically, so about 8000 milliseconds, or somewhere less than, between 1 T1 and 2 T1s. So that's not quite recovering fully, that's maybe somewhere here, right? So that's why you don't get the CSF being the brightest. But essentially For gray matter and white matter, it's proportional to the spin density, where gray matter is brighter, white matter is darker. Yeah. Okay, so in terms of the equation, again, actually we're just reiterating the same thing. So the contrast. So contrast is defined by this. You can actually optimize the contrast, but in this case, the optimization conditions are already stated, right? So TR has to be very long, and TE has to be closer to 0. So TR has to be very much greater than T1, which is approximately 5 times T1, and TE has to be very short compared to your T2 or T2 star, depending on which type of experiment you're doing, either spin echo or gradient echo. So so those are the conditions, and if you substitute those, then if you do Taylor series expansion of your expression, either the contrast expression or this one, I mean basically this, the exponential terms, if you do Taylor series expansion, you will see that this contrast expression turns out to be this plus some higher order terms, which under these conditions are negligible. Not zero, but negligible. So it all depends on the spin density weighting in your image. It all depends on how well you're meeting these criteria. If you're not meeting those criteria, then of course this term will be significant, and hence your spin density weighting is going to be deviating from what you intend it to be. Okay. So like I said, it's effective spin densities, as we talked about. It includes all those coil parameters, etc. Sensitivities. Yeah, that's pretty much it, I guess. Okay, so let's look at the other extreme now. I mean, we talked about imaging on this extreme where we wanted to see the spin density weighting. Now here, this curve is basically 1 minus C1, right? This is that's what your curve is, m naught into 1 minus e power minus tr by minus t by t1, and as a function of time, if you plot it, that's the recovery curve you would get. Now if you want t1 weighting, so basically if you wait too long, you're basically just seeing the spin density differences. Right near the recovery, here it's in this domain that you're seeing the T1 differences in the tissue, right? So you want to kind of capture at that point. So you want your TR to be very short, meaning you don't allow the magnetization to recover fully. So in that transition or mid recovery period is where you want to catch it. So short TR, and then you don't want any T2 or T2 star weighting, so you want your echo time to be very short. So that's when you would get something like this, where you have T1 weighting. Now, as you can see, the faster the recovery, the higher the signal, which means the lower the T1, the higher the signal. So your signal is actually inversely proportional to T1. Can you see that, right? The longest T1, which is CSF, is quite dark. The next one, which is gray matter, which is about 600. Well, the next one is actually gray matter is 1000, slightly darker compared to white matter, which has a T1 of 600, which is shorter, so it has more signal, right? And fat, which has the shortest T1 among the tissues that we saw, which is about 250. You see fat quite bright around the skull, right? So that is your condition for T1 weighting, which is basically short TR and short TE. And short and long is pretty much relative. Like I said, it's relative to the tissue T1s and T2 stars or T2s. Okay. So in terms of the equation, if you basically follow TR much less than T1 and TE much smaller than T2 star or T2, and you do your Taylor series expansion of your exponential, you will see that this expression, if TE is very short, meaning closer to tending to 0 in the limit, this is 1, and this is basically 1 minus TR by T1, just the leading terms, second order terms are ignored. You will see that rho times TR by T1. So your signal is inversely proportional to T1. So you can derive that from the math as well. So it's going to be. Now the other thing that I want you to notice is proportional TR. Remember the discussion that we had yesterday, in the previous class, where we said the signal was going to be, in 2D case, your signal was actually proportional to your TR. The longer the TR, the higher the signal, right? So when you actually did an experiment where your TR of your 2D experiment was NZ times TR of the 3D, the SNR expression does not tell you that you will gain the signal. It will say that the 2D's SNR is always going to be square root NZ less. But then it doesn't take into account this aspect where your signal is actually going to be higher at longer TR, with longer TR in 2Ds, right? So that's the point I was trying to make in the last class, where if you use a longer TR and do multi-slice multi-slice imaging, then you're using your dead time as well for doing multi-slices, and the longer TR is actually giving you better signal. Understood? And this is for T1 waiting. So under these conditions. Okay, so now you can actually optimize what would be for a given set of tissues. In this case, we're doing it for two tissues. If you want to optimize the contrast between two, then you can write down the expression and apply the limits that, okay, let's say you're using very short TE. Under that limit, what is the TR that you should be using so that your contrast noise ratio, or contrast in this case, noise is, in this case you're assuming, noise being equal for both tissues. So all you're worried about is the signal difference between those two tissues. So the signal difference, you can write that expression. The higher order terms are not written here. You're just using the Taylor series expansion of this, of the exponentials. And if you basically differentiate this with respect to TR, you will end up with this expression where this is the TR optimal, which is dependent on both spin densities and T1s of your tissue. T2 star is not appearing because you're saying that your echo time is very short, so T2 star effect is disappearing. Right? T is 0, or in the limit that T is tending to 0 relative to T2 star. Or basically, this ratio is getting to 0, meaning when you guys get that, right? That ratio is going to 0. Okay. Well, you can see that this is dependent on both the spin density and T1s. And if you plot that, actually plot this expression as a function of TR, then you will see that this is for CSF gray matter minus CSF, the signal, the contrast between gray matter and CSF, calculated as gray matter minus CSF. So you can see that at short TRs, where you're not letting the magnetization to fully recover, you have gray matter brighter than CSF, so you have positive contrast. And as soon as you actually go to the long TR regime, then you can you'll see that CSF dominates, so the contrast becomes negative. So there is a crossover point. So you can choose your TR such a way that there is no contrast. Well, in some cases you might want to do that. Depends on your necessity. Okay, so and in the case where spin densities are equal and there is only small difference between T1, the two tissues. For example, in the case of where there is just the edema is starting to appear in the image and in the tissue where there is lesion. If you want to detect it early on, then you want to optimize your contrast noise ratio, contrast in this case, to be able to detect that small lesion where it's starting to show edema. In that case, you might want to use this expression where for such situations you want to use this, meaning TR optimal becomes equal to the shorter of the two T1s where you're looking at the contrast optimization. So T1B here is assumed to be larger than T1A. That's because edema is basically more water in the tissue, so that means it's going to increase your T2 or and T1 of your tissue. So any change in the tissue typically leads to increase in T1 unless you are causing that change by injecting a contrast agent or something. So that's why it is modeled as such, but you can write the equations in the other way, T1 minus, meaning for any decrease in T1, then what is it going to be? Is that clear to everybody? Okay. Okay, so this, of course the left out term, what is left out? So we have discussed spin density and T1, what's left out? T2s, yes, okay. So for T2s, of course, it doesn't matter where you're imaging, but all you want to do, make sure is that it's not weighted by other parameters. Spin density you cannot avoid because it's always multiplied by rho naught. Your signal is always multiplied by rho naught. You guys realize that, right? Well, I don't know where. So m naught times 1 minus E1 times e power minus TR by T by T2, right? So that m naught is always there. That's what is giving you the signal. So spin density weighting is always going to be there in your data. So all you can do is, okay, it doesn't have any T1 weighting, let's say. So for that you have to use a longer TR to make sure you are in this regime, in this space, and you let it decay, and say basically instead of having a short TE where you're not seeing any of these T2 decay differences, you wait for a while and then sample the signal, so your TE is longer. So in this area basically, so you want to see the difference in the decay curves between different tissues. So essentially for T2 weighting, the condition is long TR and long TE. So long TR to make sure that there is no T1 weighting, and long TE is basically to get the T2 weighting. Okay. So the same thing is given in this in terms of the equation form. Essentially TR is much greater than T1, so and then your TE is long or comparable to your T2s basically. So that's your when TR is long, so this goes to 0. Can everybody see that? Okay. Now, so all you are left with is rho times e power minus TE by T2 star. That's your decay, exponential decay. And then if you work it out in terms of what is the optimal TE to get contrast between get the maximum contrast between two tissues which have T21 and T2, second one T2A and B, then once you differentiate, set it equal to 0, you will get this expression basically. And this is similar to the setup that you had in the T1 part. I mean, even there you see the exponentials. That's why this expression turns out to be similar. And even in this case, if you're looking at the case where you have two tissues with similar spin densities and slightly different T2s, then the shorter of the T2s, your TE optimal should be equal to shorter of two T2s. Is that clear to everybody? Okay, so this is the inversion recovery. You've seen this already in terms of your chapter 8 and 9, I think, where we are applying 180 degrees before 180 degree pulse to invert the magnetization and then let it relax, and then you apply your 90 degree pulse. Yes. Okay. So then now you can time your TI differently, right? I mean, in different ways. You can time your TI in such a way that there is one of the tissue signals is 0, or you can time it in such a way that there is a large signal difference between these two. So I should have included that one, but let me just draw that and show you. So your 1 minus E1 decay, I mean, recovers like that. But in the case of 180 degree pulse, it's minus m naught plus m naught into sorry, I think I missed the exponential here. Right? This is your m0 minus m naught. That's your recovery, right? So your actual recovery is like that. you will see a larger difference in the T1 tissues here when it's actually recovering from the inverted minus M naught. So that actually leads to increased contrast, T1 contrast. So MP-RAGE, magnetization prepared rapid gradient echo that you typically use in your clinicals for T1 weighting, is actually one such experiment where you actually apply 180 degree pulse first, wait for a certain TI, not particularly nulling any tissue, but just certain TI which is actually optimized to, let's say, contrast between gray matter and white matter. You can work out this equation and then say that, okay, what should be the TI so that for two tissues which have T1A and T1B, what would be the maximum contrast that I would get? The maximum contrast that I would get, what should the TI be to get the maximum contrast? So you can work out that optimization problem and then use that TI for your experiment. And that will actually lead to larger T1 contrast between gray matter and white matter compared to just the 90 degree pulse. In fact, it turns out, I think if you work it out, I think it's twice. The contrast is twice if you use the right, if you use the right TI. So that's, you can use optimal TI to get that contrast, and you can also null tissues. So this is one of the kind of example images. So you can use that to do flare imaging, fluid inversion, where CSF is suppressed. Flare is fluid attenuated inversion recovery, right? Yeah. So that's T1. That is the MP-RAGE, typical MP-RAGE image. You could do actually dual tissue suppression where you suppress. So there you have two 180 degree pulses, 180 and then 180, and then you have 90 degree. So you can write that equation, what that equation turns out to be. Under certain conditions, of course, you have to assume that TR is long, and it will be simplified. If your TR is very short, then it gets a little bit complicated. But under simplified conditions, you can derive what that equation is going to be. Then you derive what should your TI be, TI1 and TI2 if you have two inversions. Then to null two tissues basically. In this case, to null one tissue, you just need to know T1 of that one tissue, and what is TI equal to in the case of one pi pulse? Right. So T1 times log of 2, natural logarithm of 2. So that should be your TI. For two inversion pulses, what would be for those? It will depend on those two tissues that you want to suppress. So this is suppressing white matter and CSF. This is suppressing gray matter and CSF. And then you can also suppress fat. This is without suppression. This is with suppression. So you can do all sorts of things with inversion recovery. It's one of the very widely used application. Okay, so the other one people use to generate contrast. So right now, so far we've talked about spin density T1 and T2, and then T2 and T2 star are quite similar. So the same expressions are used more or less, except for the spin echo versus gradient echo. That's all. So you can relate both of them; they're analogous to each other. Then we talked about inversion recovery, which is actually a consequence of the pulse sequence, the pulse parameters that you're using to generate increased contrast. Right? You're using the T1 property, but you're able to generate increased contrast based on the pulse sequence that you implemented. Here you can generate contrast between tissues by injecting exogenous contrast agents, which would change one of these tissue properties, either spin density or T1 or T2 or T2 star. So typically T1 shortening agents have been used. When you inject that or when you insert that into the body, either typically through direct injection, it would change the T1 property of the tissue where you injected it. It can also change, depending on the property of the contrast agent, it can also change the T2 or T2 star. Typically the change is empirically expressed in this form, where the net T1 or the effective T1 is the summation of the T1 plus the concentration of the contrast agent times alpha 1, which is a property of the contrast agent, which is the relaxivity of the contrast agent. So, so per unit concentration of the contrast agent, how much would the T1 relaxation be? So that's what this is. Similarly, you can write for the T2 as well. And the gadolinium based contrast agents which are widely used today for clinical imaging for looking at cerebral perfusion or cerebral blood volume, etc. They change both T1 property and T2 and T2 star properties. So which property you actually want to utilize depends on you end up using actually depends on the type of imaging parameters that you would be using. So if you want to capitalize on T1 effect, then what are the parameters that you would use? If you want to see T1 change, what should your sequence parameters be?
Short TR, short TE.
Right. So if you use short TR, short TE experiment and you inject the contrast agent, what you would see is the T1 effect of the contrast agent. Because you're using short TE, so you won't see any T2 or T2 star effects. If you want to see the T2 or T2 star effects, then you use relatively long TE or long TR and long TE, right? So depending on the experimental parameters that you would use, your signal effect of contrast agent would differ basically. Okay, so it's being used for tumor imaging to highlight breakdown of your blood-brain barrier. It can also be used. It's widely used for looking at perfusion, tissue perfusion, and you could also look at vessel wall lesions which would be enhanced because you're generating contrast between the interior of the vessel and the vessel wall. So this is one of the examples in tumors. So you have the same subject before contrast injection, after contrast injection. You would see on the right the tumor which is right beside the ventricles is highlighted, and you can actually subtract and see what the blood circulation of that or blood supply of that tumor is, and then that can inform the surgeon to look at the draining and the feeding vessels and then say, okay, you want to either cut them or leave them alone and avoid them when you're doing the surgery, etc., etc. So it is useful for the surgeons before they actually embark on the surgery to know what is the blood supply of the tumor. That's one application. This is angiography in general is one of the applications where injecting the contrast agent allows you to see a lot more compared to just a normal angiography which is based on just the flow of blood, which you would come to in chapter 24 in the next few sessions. Another one is actually looking at temporal injection of the contrast agent, temporal take-up of the contrast agent to look at cardiovascular function. And you can actually plot the signal intensities. Actually, this is corresponding to this one, where contrast agent take-up is looked at quantitatively to see a benign tumor takes up more of contrast agent compared to the non-benign tumor in breast imaging, basically. So coming back to the contrast to noise ratio aspects, where when we talked about different ways of generating contrast, mainly a few of them at least, and we also discussed what the contrast to noise ratio concepts, why noise becomes important and why the object size becomes important. If you notice, if you change the resolution, the contrast to noise ratio of an object, as long as the noise is not changing, doesn't change. The contrast to noise ratio, as long as the object is occupying full voxels, meaning there is no partial volume, meaning the one voxel is occupying the whole object. You will see that there is, let me see how best can I say this. So if an object is occupying complete voxels, let's say 10 by 10 voxels, it's a cube, it's a square. If you change the resolution to such that the object is actually now occupying 5 by 5 voxels, does the contrast change, contrast noise ratio? Assume that the noise is same, meaning noise same, meaning for this experimental noise standard deviation is the same. The number of samples has changed, so let's write that out. So you have SNR that's proportional to delta x, delta y. Let's just write two dimensions nx and y times ts, and then your CNR is S 1 by SA by sigma minus SB by sigma times square root of n voxels. Right. So now the scenario that we are considering is delta x becomes delta x by 2. Sorry, now the scenario we are considering is it's 2 delta x, and then this is 2 delta y. Now does the number of voxels change? Number of sample points change. Like, so if you assume the number of sample points change, which is nx by 2 and ny by 2, right? Because now the voxel size is doubled, so your number of voxels have changed. Ts is remaining the same. So what is the effective increase in SNR? Am I right? It's factor 2, right? Okay, so let's look at that here. So the new CNR is going to be 2 times SA by sigma minus SB by sigma times square root n voxels. N is basically now nx times ny, but not that one, it's just the nx dimension, n prime, let's say. Now it's actually twice, right? So this is under square root, so that's basically 1 by 2 times 2. This gets cancelled, so CNR doesn't change. Actually, there is one mistake in this. I just realized that. Can anybody point that out? Let me think about that for a second. So your field of view hasn't changed. So if the field of view hasn't changed, then no, I think it's right. So sorry, there's no mistake. I'm sorry.
What about the visibility factor? You said
Actually, it is the visibility that I'm talking about. My mistake. CNR actually changes. I'm sorry. That's my mistake. CNR actually does change. It's the visibility, that's square root n voxels, that does not change. Okay, it's not. Then I guess that's a typo. It should be visibility. It's not CNR. CNR is independent of the resolution, as long as its object it's occupying full voxels, meaning there's no partial voluming. In the case of partial voluming, that doesn't remain true. So as we'll see. Is that clear to everybody? Okay. So that is visibility. Okay. So in the case of partial voluming, actually you have 2 tissues occupying the same voxel. So you have the signal is added up from the two different tissues. Now the question is whether you will be able to make out the presence of the second tissue. Can you or can you not? So that is the question essentially. Or to be able to do that, what can you do in your experiment to make sure you are able to do that? And partial voluming is a practical aspect that you would face in your data collection, because you always have a finite resolution, and your objects of some of the objects will always be smaller than the voxel that you're imaging, voxel size. For example, if you're doing 1 millimeter cube voxel size, the capillaries which are much smaller will always be partial volume. Now, whether you can see the effect of the capillaries or not depends on how you gear your experimental parameters to sensitize yourself to that contrast. Or let's say if you increase your signal resolution, then can you actually make yourself sensitive to the presence of those smaller vessels, so that you can evaluate that by looking at the contrast to noise ratio and the signal from those vessels relative to the signal of the background. So here is one example where to show the benefit of higher resolution. So if you have two scenarios where you have the well, in fact, it's probably easier for me to just do it here. Let's say you begin with this voxel, and this is tissue A and tissue B. The length of this voxel is delta x. Okay. Now you change your voxel size to beta times delta x, but this A remains the same. It is still occupying the voxel, but now it's a smaller voxel. So let's say the proportion or the length here is alpha times delta x. Here it's the same length, so alpha times delta x remains, delta x being the original x. Okay, so here it's 1 minus alpha times delta x is the signal from this part, whereas here now this is the signal from the whole one is beta times delta x, right? If this tissue B was occupying the full voxel, then the signal would be beta times delta x. Correct? But of course the alpha times delta x is being occupied by A, so you subtract that. That's your signal from the new voxel. So signal, the contrast in this case is what? S. Okay, so yeah, that's right. So alpha times delta x minus SA minus SB, right? Minus of beta times, sorry, there's no beta here, it's just B. So 1 minus alpha times the point that I'm missing here is the next voxel. This is just totally tissue B. Okay. That's the point I was missing there, just to give you the scenario. So it's the contrast between these two that we are calculating, and in this case that's the same here. Okay. So the signal in the background will be delta x, that's SB, and then from this voxel it's going to be this minus S of, okay, I'm just trying to get the notation right. I mean, this is already explained in the textbook, so I guess it's not a big deal to do that. Okay, so SA is the signal from tissue, SB in this case. Okay, I think now I have my bearings now. Okay, now I get it how to do this. So it's SB times SB is your signal from B tissue B. SA is signal from tissue A, and your voxel volume is basically given here. So background tissue voxel is SB times delta X minus, so this voxel, which is SA times alpha times delta X plus S okay, so if you work that out, you just get contrast is basically alpha minus SA times SB, or the way here is basically, so you can see that this SB and this SB gets cancelled. All you have is alpha times SB minus SA here, the way I wrote it. There it's written as SA minus SB, basically it's defined the opposite way. Now you will see that if you write it for this one, also it turns out to be the same expression. So let's write that out. So the background voxel now is beta times delta X times SB minus SA times alpha times delta X plus this one. This is the volume of the next one, this remaining one, right? So that's SB times beta minus alpha times delta X. So SB times delta X and then SB times beta times delta X, that gets cancelled. All you have, not this one, sorry, this term. So this beta and this beta, those are the same terms. So all you will end up with is the same thing, SB minus SA, because this SB is positive because of the minus alpha, this one is negative, so that's what you would end up with. So the contrast or the signal difference doesn't change. However, because you can now you basically you've reduced the voxel size. You can reduce the voxel size in two ways. One is reducing the field of view. The other one is reducing the number of samples, or increasing the number of samples, I mean. Keeping the number of samples same, reducing the field of view will decrease your voxel size. Keeping the field of view same, increasing the number of voxels will decrease the voxel size. So both of them will have the same effect. It's this. Originally you had this, you can reduce that to this, keep the same number of points. So you're just reducing that and just sampling this. Or you keep the same and then you just sample more number of points. This is spatially that I'm talking about, not in K-space. Just don't confuse yourself between those two, okay? Not the K-space part. So, but the effect of those two is different on the effective contrast to noise ratio. Because in the first case, where you change the field of view, the noise doesn't get changed because the number of samples you're sampling in both experiments is the same. Whereas when you sample or change the number of samples, then your noise actually gets factored by the number of samples, the increase in the number of samples. So if you double the number of samples, then your noise is sigma naught divided by square root 2. If you triple or any other factor, basically it's just square root of that in the denominator. So that is where by increasing the resolution, even though your signal is actually weighted by a smaller meaning beta, meaning lower signal, you're decreasing your signal, whereas but you will end up with an increased signal to noise ratio because of an increased contrast noise ratio because of your increased number of points. So even though your signal to noise ratio might be going down, because of the increase in the number of voxels, you're able to get a better contrast noise ratio. So when you change the field of view, I mean basically in either case, essentially you're changing your voxel size smaller, right? So you're increasing your resolution. So signal voxel size has gone down, so signal has gone down. Signal to noise ratio, noise remains the signal to noise ratio would also change, but in this case signal to noise ratio actually even also goes down, because here let's say you went from delta x to delta x by 2. Okay, let's take numbers. I think that's probably easier to understand. So if you go this, you can do that in two ways. In either case, your signal to noise ratio is going to be worse. Right? So now you can either change nx or your TS. So delta x by 2 square root, so let's say that's 2nx. So that becomes your SNR is basically, you increase your number of points, so your SNR has gone down by 1 by square root 2. Let's say, either way, even if you change your TS, that's the same scenario, right? So it's always what's by square root 2. However, the point I was trying to make is that your contrast noise ratio you're going to gain because of your increased resolution if you have partial voluming. Is that point clear to you? Even though you lose signal to noise ratio by going to higher resolution, your contrast noise ratio you can gain in case of partial voluming. And we saw just before this discussion in terms of the visibility, also if you increase your resolution, or if you change your resolution for that matter, you won't have any change in your visibility of your other objects which are occupying full voxel, right? Is that clear now? Okay. So partial voluming, of course, any low resolution would lead to partial voluming, leads to blurring basically. So just on the top you see that image where it's a very highly low resolution image, so you just cannot make out the details. And then the bold effect, basically averaging of the signal due to of different types of tissue will lead to effective T2 star or T2 prime decay. So that's the basis of your bold imaging, where you're looking at changes in the intra and extravascular signal changes due to functional activation. Basically increase or decrease in deoxyhemoglobin is going to cause a signal change. You'll come to that in chapter 25. Excuse me. So because that a big voxel contains all these different types of tissue, you're getting a vector addition of the or complex addition of all the signal components within that voxel. Similar case you can see that more explicitly in case of chemical shift, and I think this number 1 and these two are essentially the same. I mean, more or less all of these are referring to the same, essentially a consequence of signal summation of different types of tissue which have different phases. So either it can lead to signal cancellation or signal addition. So you'll see an oscillatory behavior. Now chemical shift is one explicit example where we'll come to that in the next class, I think. Fat, due to its material property, has a finite shift in its frequency, resonance frequency compared to the surrounding tissue relative to water essentially. So because of that, if any voxel contains both water and fat, because of that finite signal difference, off resonance, basically the precession frequency of fat is slightly different but fixed. It's not spatially varying. Within fat, the precession frequency of that is different from water. So because of that, they will it's like two rotating vectors which are slightly out of phase, out of sync with each other. So at some point they will constructively add up. At some point they will subtract out, basically 180 degrees out of phase. So they will subtract out. So you will see this is essentially a signal from a voxel containing water and fat, this decay that you see. But this decay that you see is due to the T2 decay of the overall voxel, both water and fat tissue. But this oscillation that you see is because of that particular vector addition and subtraction as they come in sync and then go or get out of sync, basically. I think you will see this example in the next class illustrated much better. Okay. So partial voluming, of course, this is a problem because it used to be a problem, and in fact today you use this information to actually find out what is the water fraction and fat fraction given in a given voxel.
So I think it's always nicer to have not have partial voluming, right?
Ideally, if you have high enough resolution that you want to see the tissues occupying distinct voxels. If you do have, but practically speaking, for very small structures that is not possible. For example, capillaries, or if you have a reasonably large voxel like you do in functional MRI, then you will always have this partial voluming. But the fact that you understand the effect of this partial voluming will lead to correct interpretation of that signal. Otherwise, you won't be able to correctly understand what is in there within that voxel.
It's always nicer to have more voxels, right? So partial voluming is not there as much.
True. You have, but then of course, voxel volume, you cannot have infinitely small voxel because you don't have enough signal from that voxel. So, of course, so it's a balance between what you can do versus what you want to do. What is the trade-off that you can live with? So we talked about in the beginning slides SNR in phase. Well, this slide is more or less summarizing the effect of basically phase signal to noise ratio. One important point that I want you to draw is that even in some cases, even if the magnitude does not have contrast within the image, phase can lead to contrast. Now, in all the discussion that we had so far, we've assumed ideal situations where ideal experimental conditions. Like I said, if the conditions are not ideal in some cases where, for example, field is not homogeneous, so you will have phase effects coming into picture, meaning your phase would be finite, it's not zero. So that phase, you will see that the tissue properties, some of the tissue properties can be reflected in phase. One of the examples is, of course, susceptibility that would cause small shifts in the local resonance frequency, and you would see that phase shift. And then the other one is chemical shift, which is mentioned in this slide, where you can see the chemical shift effect in the phase images. So like we said, they'll get in phase and out of phase, right? So if you have within a voxel, so if you have a fat and a water voxel, so fat would be processing, let's say, slightly faster compared to water. Okay, so these would either come in and sync and go. That's what you saw in the previous. Whenever they are in sync, they will add up, and then wherever they are not, they would get a lower signal. And this is basically the T2 decay of that voxel. This, of course, you cannot escape that T2 and T2 star decay, right? But this is your because of this addition. Now, if you have two voxels which just have fat and water, this is if this was within a voxel, you're getting added up those two. I mean, you're adding up those two vectors. But if this was individual voxels, then in the phase image, you would be able to see that this phase is slightly off from this phase. I would show you these images in the next class. I don't have them ready in these slides, but so that's where phase image can show you the differences between fat and water, or chemical shift tissues versus non-chemical shift, tissues which do not have chemical shift, and then like I said, susceptibility is one of them. So the other ones are, well, phase is also used for other effects, for example phase contrast imaging, which is used for blood flow quantification, etc. All of these are covered in those respective chapters, which in the next class we are going over the we'll go over the chemical shift effect that we just talked about in much more detail. Okay, I think that's the conclusion of the class today. Thank you. Any questions so far?